We're live. We're live. We're waiting for the news from the peoples that we are actually live. I see myself live. I think we're good. Oh, somehow chat is disabled for the stream. Interesting. We'll see what happens there. Anyhow, I did not disable the chat. If somebody can re-enable it, that would be fantastic. But we have our chat room at twis.org/live if you are interested in chatting along with this show. The show that's beginning in 3, 2. This is TWIS. This Week in Science, episode number 709, recorded on Wednesday, February 20th, 2019. Dark energy and redshifts. Hey everyone, I'm Dr. Kiki, and tonight on This Week in Science, we are going to fill your heads with sharks, old sperm, and space. But first.
Disclaimer, disclaimer, disclaimer. Have you ever wondered what things were like in the good old days? What did they do all day? How did they have fun? What did they eat? Whatever you imagined about that time and those days was most likely totally wrong. Chances are that life was a lot harder, but people were still not so much different than they are today. Chances are bad that the diet you were eating based on any peoples of the past actually resembles a diet of anything other than the current humans who read the same book, magazine article, or watched the same talk show nutritionist infomercial. Most diet data on days gone by is based on what diet data we have found so far. And despite the many revisions of ancient diets that have come from an increased supply of discovery, most diet fads stick to what they've been hearing from 10-year, 20-year-old news, sticking instead to the myth of the good old days. In fact, fake ancient diet fallacies don't stop with people. It's a fad with people's pets as well. Dog food pitches ancient diet all the time, telling you your dog needs meat. After all, your dog descended from an apex predator. As if this was yesterday. As if your fur baby was just weaned from the wolfy wild. As we will report later in this episode, nothing could be further from the truth. In fact, your furry friend might be better evolved to enjoy a veggie diet. What do you think? All this and much more furry fun ahead on This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I wanna learn everything. I wanna fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I wanna know what's happening. What's happening? What's happening this week in science? What's happening? What's happening? What's happening this week in science?
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We are back yet again to talk about all the science that we enjoyed and want to talk about this week. So it's just fun times with science. I have stories. What do I have stories about? I have stories about gene drive and the great white shark genome. Those stories don't necessarily go together. Yeah. And we also have an interview this evening with a FermiLab researcher to discuss the dark energy survey and its findings. Justin, what did you bring for the show?
I've got vegetarian dogs of the Neolithic, native California shrub used by Native Americans to relieve inflammation. Could be a treatment for Alzheimer's, and cost-benefit analysis to industries that kill more people than they employ.
Cost-benefit analysis is that's not the two industries. Okay, never mind. Moving on, Blair's Animal Corner. What's in it?
Oh my goodness. Well, like Justin, I also brought news about a shrubbery, but this one is about deer. I also brought a story about cassowary casks. And of course, I brought some old sperm.
Of course you did.
Of
Of
course.
course you did.
I mean, yeah, what else would I expect from you when it's time for a show? But as we jump into, I am so happy to remind you all that if you have not yet subscribed, please do so. You can subscribe to This Week in Science, all good places that good podcasts are found. So iTunes, the Apple Marketplace, Google Play's podcast portal, Stitcher, Spreaker, Spotify, Pandora, TuneIn. Just search for This Week in Science. You can also find us on YouTube and Facebook, or you can visit TWIS.org. All right, let's jump in to our interview for the evening. I would love to welcome Dr. Antonella Palmese to the show. Dr. Palmese is a postdoctoral researcher associate at FermiLab, and at FermiLab, she is part of the Dark Energy Survey, and she does observational cosmology. Welcome to the show.
Thank you. Thank you for having me here.
It's wonderful to get you on the show to talk about this Dark Energy Survey. I mean, we have these names for things, the Dark Energy Survey. I find it very interesting that the survey itself, though, is looking at light. To tell us about this dark energy, can you explain what the Dark Energy Survey is?
Sure. So the Dark Energy Survey is a large-scale galaxy survey. So it just finished actually last month. It was the 9th of January, 2019, after almost 6 years of observations. And we took images of 5,000 square degrees of the southern sky. So this is about 1/8 of the whole sky. So it's a lot. And sorry?
I was wowing because, yeah, usually we're getting a pinpoint of a sliver of a tiny aspect of something, and then there's a billion galaxies there, which is really cool. But then there's all this other that we're not looking at when we're that dialed in and focused. So this is a huge, wide scan of space.
Yes. So usually when you go into some smaller area, you're looking into deeper things. So you're trying to image the faintest thing of the universe. In this case, we're also going deep as compared to the ancestor of the Dark Energy Survey, which was the Sloan Digital Sky Survey, which imaged a lot of the northern hemisphere. But that only goes to, say, redshift 0.3. We'll talk about redshifts maybe more in detail later. And with the Dark Energy Survey, we go out to redshift about 1. So we've taken images for hundreds of millions of galaxies. And so this is what we're currently taking care of, like trying to analyze all of this set of data that we have. So at the moment, we analyzed only the first year of observations, and we have 6 of this. Some results are already out using the first 3 years of observations. So these are really exciting, but there's still a lot that we have to analyze in terms of cosmology and how to understand better what dark matter is and dark energies and so on. So what we do with the Dark Energy Survey is we take just images. So this means that we are looking at some colors of the galaxies. In particular, these are in the optical and the visual bands that we can see with our eyes, and towards also the near infrared a little bit, so that we can go towards higher redshifts. So all of these galaxies that are farther away. And so this is how we try to trace the dark matter in the universe and its evolution by looking at these galaxies that are also much farther away from us. We have done actually a lot of science with DES. We have done some cosmological results, which is what we were expected to do with this particular survey. But at the same time, we've also done some, say, non-dark energy discoveries, which include dwarf galaxies, gravitational waves, and so on, and stellar streams. So it's been very exciting, you know, like you get a large data set and there's just so many things that you can learn with that. So I don't know if you want to pop up some images. There's so there is a footprint image, which shows like the tank shape of the Dark Energy Survey. So I don't see the image. Am I meant to see it? Oh, okay, here. Okay, so this tank, this is the shape of the footprint of the Dark Energy Survey. This is what we have observed, well, first during the first 3 years of observations, but also during the full observation time of almost 5 years, because we're trying to make 10 passes over this whole region so that we can go deeper and deeper. This means like we are increasing our exposure time so that we can see the fainter things.
Right. So you're just passing over the same areas multiple times and allowing the light to be additive.
That's right. Exactly.
Okay.
It's like exposure time in your own camera, pretty much, but just much better. And so then you can see how we started with this science verification SV. That's what we got in 2012 when we got the first light with the dark energy camera, which was actually mostly made here at FermiLab. And then it was sent over to CTIO, the Cerro Tololo Inter-American Observatory, which is in Chile, close to La Serena. Yes, and you can see this is the dark energy camera. So this is actually on the focal plane. That's where you see all these CCDs. I think these are 74 CCDs. Some of them died. One of them came back to life at some point 2 years ago. I don't know why.
Fickle technology.
Yeah, so this is how it looks. So the reason why, one of the reasons why this camera is so special is because it has a very large field of view. So this focal plane that you see here, this camera that you see here, is able to take an image with just one pointing, which is about 3 square degrees, which is roughly 14 times the full moon. So this is very large. Yes, this is huge. And this is one of the strengths of our wide survey, and also one of the strengths of our gravitational wave follow-up, so that we can actually search for the candidates, the sources of gravitational waves very quickly, because we have this very large field of view. And so from the footprint before, we also saw that there were some smaller pointings, and these are the supernova fields. So we have a wide field where we're taking images for these hundreds of millions of galaxies, and then some smaller fields over which we focus. And we have focused because it's over, unfortunately. Still think it's on, sorry. But yeah, we were taking images almost every week over these yellow small fields that you see there. And so that we could see all of these supernova events coming up. And so identify supernovae and then use those for cosmology.
Were these areas where the supernovae occurred, where you were studying them, had supernovae been identified there, and so that's why you focused there? Or did you just randomly pick some areas of the sky and say, we're going to sit here and just wait until a star goes supernova?
Yes, that's pretty much it. Well, in a way, the survey was defined taking into account different things. For example, overlap with other surveys. As you can see, on the northern part, you see this gray and green areas. This is other surveys. I think that the gray area is the BOSS, as part of the Sloan survey. And so you want to have some overlap with these previous surveys. That is always good for calibration. For example, or like you already have some spectroscopic redshifts, some very precise redshifts from this BOSS data, for example. So that could be helpful in combining the data sets. But no, there was no particular reason. We just wanted to define some areas that were observable for most of the time when we are up observing in the sky during the observing runs that we have. And yeah, just take observations week after week. And there would be new supernovae coming up all the time.
Something else that really stands out to me is the fact that, I mean, this is the southern hemisphere. We're looking at the southern sky, and all of the BOSS survey, the gray and the green regions in the image that you've given us are in the northern hemisphere. Is this one of the first southern hemisphere surveys?
Yes. So in terms of this very large photometric survey, so photometry, so we just have some filters. We will see later how these filters look like. Instead of having like a full spectrum, the full spectral energy distribution of the galaxy, we just have some particular filters, so some particular colors of the galaxies. So yes, in the northern, we had SDSS. That was the first big galaxy survey, and this is the second one. But something that we're really missing in the south is actually spectroscopy. So something that allows us to look at the full spectrum of the galaxies and so define their redshift and thus their distance very precisely. So that's something that is actually missing in the south. We have some, but they're very shallow. They only see the very bright galaxies.
So let's talk about redshift for a second before we go much further, because you've mentioned it a few times. How is redshift important for what you're studying?
Okay, so let's first say what the redshift is.
Yeah.
Okay, so this works more or less as the Doppler shift that we all know from the example of the ambulance. When it's coming towards us, has some frequency for the sound, and then when it's going away from us, it has another frequency. So when it's coming towards us, the frequency becomes faster, so it's higher energy, let's say. That's the same thing with the photons. When something is coming that is emitting photons and it's coming towards us, we get a higher energy radiation, so like what we call a blue shift. So the energy is shifted towards the bluer colors. And when it's going away from us, we get a different frequency again, but in that case, it's towards redder wavelengths, so lower energies. And so that's a redshift. So in the case of the galaxies, because of the expansion of the universe, this is something that Hubble back in the 20s found out, is that most of the galaxies are actually receding from us. And this is because of what was called then the Hubble expansion. And so what he realized is that the velocity of recession from us was actually always proportional to their distance from us. So in a way, the redshift of a galaxy is telling us something about its distance. And so this is what we try to measure using the dark energy survey as well. So there was a figure there. I think it's called redshift.
Okay, I'll bring that up just a moment. Yeah. I'll see if I can get to these things quickly enough.
But if the red shifting or the expansion is proportional, or the amount of red shifting is proportional to how far away something is, that kind of indicates that it's happening everywhere at once at the same rate.
Yes, that's right. That's right. That's one of our cosmological principle, is that the universe is actually homogeneous and isotropic, and this expansion is also happening isotropically everywhere in the same way, the same rate. Yes.
Is this something that's up for debate, though, whether or not the universe is homogeneous in this way?
Yeah, well, it is. Of course, it's not on very small scales, because we have Earth, we have the sun, we have the galaxy, we have clusters. So we know that on smaller scales, that there is clumpiness in the universe, right? But if you go on large enough scales, we know that it becomes homogeneous. But then there are some theories that say maybe it's not completely, so maybe we have to measure that better. But let's say that it is.
For the sake of argument, we'll just say that.
Well, but I mean, is there like, how do we know that we're not essentially expanding away from our sun at the same rate that the rest of the universe is expanding? Because it's actually as big as it is on a large scale. On a smaller scale, it's actually not that much. It's taking it's moving really slow.
Yeah. Yes,
essentially. So it could be happening all around us, but we would never have enough time to notice it.
That could also be. That could be a possibility. Yes, that's true. But usually what we consider is like our galaxy is actually not part of this expansion. That's what we usually consider. Yes.
Does that make us the center again? Once again, do we get to be the center of activity?
No. No, we don't want to be the center. That's why we say we're not special. That's why we know this is happening in the rest of the universe.
And some of it is dramatic, though, because the further away it is, there's like a multiplier, because then it's also moving away from the thing that was closer, and then it's moving away. So it's as much as this is accelerating is the word that's used, it's actually consistent everywhere. It's not that it's accelerating, it's just that stuff that's already further away has all the points in between that are slightly expanding away from each other. And so it looks really big and fast on a deep scale. But the closer to home you get, the less it's really, it's tiny, right? Isn't it? I don't know how you quantify what the quantification is of this growth, but it's really a small movement of things apart, right?
Yes. So the Hubble constant, now we know it's around 70 kilometers per second, but per megaparsec.
And for those of you who aren't familiar with a megaparsec, what's a megaparsec?
Oh, good question. I never remember.
If you're not familiar with a megaparsec, go read Douglas Adams. No, I don't.
But that's like, I mean, it's not. It's a measurement of speed of light over a distance, but it's many. Is that how that works?
Sorry, good question.
Okay.
According to Star Wars, parsecs were a measure of time, but we now know that parsecs are a measure of distance. That I am
Millennium
sure
Falcon
about.
can do, yes, but but it's those kilometers are over a immensely mind-bogglingly vast amount of space-timey distance.
That's right.
So it's really slow. It's just dramatic because space is so big, and the further away you look, the more it's had time and space to move.
That's right. Okay. Yes, it's mind-blowing, right? That's one of the things that got me into this.
So when you're looking at redshift, when you're looking at this photometric data and you're considering what all these frequencies of light are telling you, what do you consider, and what does it tell you about the age or the distance of certain galaxy clusters and how they're acting within the universe?
So in this figure here, what is showing is the spectrum of a galaxy being redshifted at different redshifts. So say a redshift 0, so that where it says the Z equals 0 is the blue line. And then there's just the same galaxy, different redshifts. It's just at different heights, just for figurative purposes. And so, as you see, the galaxy spectrum has a lot of features. One of the best feature, probably the main feature that we use for determining the redshift of the galaxy is this 4,000 angstrom break. So this is a feature that we see in the spectral energy distribution of the galaxies, of almost all galaxies, is that it's like a break in the spectrum around 4,000 angstrom. And so we see this in most of the galaxies. And so by looking at the position of this break, we can tell what the redshift of the galaxy is. So this is how you see that going through the different, what we call filters that we have in DS. These are the G, R, I, and Z filters. So this means that we're not looking at all these features, the single feature that we see in the spectrum, but we're looking at all of the photons that have that range of energy in G, in R, in I, and Z. So we're not able to discern all the small features, but we're able to see if between one filter and the other, we have a big difference in the flux of the photons that we receive. So if, say, there is a big difference between G and R, we can say that that galaxy is at a smaller redshift than a galaxy that has a larger difference between I and Z, for example. So this is how we try to estimate what we call the photometric redshifts, which is different from what we call the spectroscopic redshift, which is what we can compute when we have the full spectrum of the galaxy. And so in that case, we can fit the whole spectrum, and it's much easier to get a precise and accurate measurement of the redshift. But in our case, we only have 4 filters.
And is this limited by what you can what can be fit into the CCD, like into the actual technology on the in the camera? So it's like RGB. you've got certain filters, and that's what and that's the light that can be collected, right?
That's right. You have certain filters, and to do spectroscopy is much more complicated. It's just a completely different instrument. You cannot use the same imaging detectors that we use in this case, and it just takes much more time. So if you with the imager, we take a big chunk of the sky already with just one pointing. When you want to do spectroscopy, you have to for example, you have some fibers, so you can point a fiber. Each fiber on a particular galaxy and stay there for longer. So it's much more expensive, right? You already have to know where the galaxy is so that you can point your detector there, versus just take an image, everything that's there you detected. And so in this way we can look at many more galaxies. So the statistics was the reason behind doing an imaging survey versus a spectroscopic survey.
And so we've, like you said, there have been many discoveries, like even matching. There was work that was done with this dark energy survey that matched up with some gravitational wave data. And so there's lots of crossover, but what is the main intent of this dark energy survey? Like, you're looking at this photometric data, and what will this 6 years of data actually tell you?
So the main goal is to actually try and understand how much dark matter we have in the universe, how much dark energy we have in the universe. Well, I would say what they are, but I don't know. Well, we can measure how much we have and how they behave, but who knows if we'll be able to understand better what they are. So we have different what we call cosmological probes, and these are the clustering of galaxies, the weak gravitational lensing, galaxy clusters, and supernovae. So these are the 4 ways for observational probes that we use to try and answer these questions. So I can go a bit more in detail into these probes. So we have one of my favorite ones, which is galaxy clusters. So the galaxy clusters are the largest gravitationally bound structures that we see in the universe. I think like one galaxy cluster has a mass that is like 10 to the 14 times the mass of the sun. So it's huge. It can be hundreds or even thousands of galaxies bound together gravitationally. And so we can use these large structures to try and probe the peaks of the dark matter density of the universe. So this is one of the ways that we do it. We try to count how many clusters and what mass they have in a certain volume of the universe, and so we can tell how they are expanding and how the universe is expanding and how the structure is behaving, say, between redshift almost 1 and today. So this is one. The other one is weak gravitational lensing. So the light, we know that for general relativity, the light can be bent by a gravitational field. So say I'm looking at the galaxy that is far away, and we see the light coming towards us, and along the line of sight there is structure. So by looking at the distortion that we see in this, what we call the source galaxies, we are able to reconstruct the matter that is between us and the source galaxies. Then with supernovae, you have a luminosity distance measurement, because the supernovae tend to have more or less the same, what we call light curve, the same luminosity over time, and so intrinsically. And so by looking at how dim this thing is, we can say whether it's farther away or closer to us. And so by relating this distance to the redshift of the host galaxy, which we can also measure, then we can measure the Hubble constant. And this is also something that we did with gravitational waves. It was not the most precise measurement of the Hubble constant, but it was, a new technique used for the first time. And then we have galaxy clustering also, that we can ask, okay, we have a galaxy here, what is the probability of having another galaxy at this distance? And so by trying to understand how matter is distributed within the universe and at different redshifts, we can again try to reconstruct the dark matter density of the universe and its evolution. So I can show you one plot. I don't know where you, if you want to talk about this more. There is a plot that is the results from the year 1 dark energy results, but you also popped up another image. Maybe you like that more.
No, it's fine. Yeah, whichever you want to talk about. I'm interested in you're talking about the probability of galaxies being clustered together, and dark matter. I mean, no, I know recently there was a survey that discovered, we've been trying to figure out where's this missing percentage of baryonic matter in the universe. And so it was like, oh, it's in the dust in between all the universes. And they're finally able to figure out it's lost in the dust. Is there a proportion of, I guess, dark matter dust that's expected as well? Like beyond even, this galaxy clustering? Or from what we've seen, do you expect most of the dark matter to be sticking with the big, massive objects?
Yeah, I think that most of the dark matter is stuck with the most massive objects, but of course, there's also what we call filaments structures that people have tried to look into this within the dark energy survey, by looking at voids and filaments of this large scale structure. But yeah, I'm not sure about the results that they got there. I know about this other study about the baryonic matter, and that's something that is very relevant also to what we study. And it's striking that we are still debating about 70% of the universe is dark energy and 30% is dark matter. But wait, even the 5% that we are meant to be already aware of, like all the baryonic matter, we cannot find even that.
It's like, we can't find the baryonic matter. How are we going to find the stuff we can't even see? we need better instruments, obviously. So let's talk a bit about the year one results and kind of what came out of that assessment.
Yeah, so this is one of the money plots from the year one results that we had. So this is only taking into account the galaxy clustering and the weak gravitational lensing. So we're still not taking into account other two cosmological probes. Unfortunately, we're a bit late with the galaxy clusters cosmological measurements. But the great thing about that is that we will have similar constraints to the other probes combined. So what our cluster working group coordinator likes to say will be last but not least. So this will be an interesting result. Will come out soon. So here, what we're showing in blue is the constraints. So how big the constraints are in the cosmological parameters. In this case, we have 2 of the 6 cosmological parameters that are usually taken into account. So how big these contours are shows you how precise your measurement is. So the first thing that we look into is that, okay, the Y1, DES Y1 contours are more or less the same size of the Planck contours. Planck is a space mission that looked at the cosmic microwave background, and it's just striking that even from a ground telescope and just 1 year of observations, we are able to get something that is similar to what Planck got. And this is just great. So what we're showing here is on the y-axis S8. So this is telling you something about the clumpiness of the matter in the universe. And then on the x-axis, we are showing omega matter. This is the density of matter, everything. So dark matter plus baryonic matter in the universe. What is very interesting to see is, okay, these 2 contours, Planck and DS, might look a little bit off, but they're actually consistent within each other. They're still overlapping. So our statistical measurements cannot claim that there is no agreement between the 2 at the moment, at least. And so what is really great to see is that Planck was observing the cosmic microwave background. So that's something that was emitted more than 13 giga years ago. 13 billion years ago, right? And DS is observing the universe in the last giga years. And we're still getting something similar. And this is just great. So it's just like saying we put a seed in the grass and we want that to become a tree.
But in this case, apparently an avocado tree.
Yeah, and we say it's an avocado tree and it's going to be this high. And then when it grows, we find that it's actually that high. So this is just striking. And then, this is just year 1 data. We'll have it's year 6 data, but really we kind of almost lost one season because of weather. So it's year 5, really it's 5 years of observations. And, we don't know where these contours are going to shift. Will they shift closer to Planck, closer to what is our standard model, the concordance model, what is called the lambda CDM model, in which the universe is made of with this lambda cosmological constant, and of CDM, which is the cold dark matter, or maybe will it shift to something else? This is the question that we hope to answer hopefully in the next year.
That's always the most interesting thing, when it's this preliminary analysis, right? And so you're just looking at one subset of the data, and while there's agreement now, it could end up completely disagreeing later, or it could end up staying where it is, or it could end up shifting into even more agreement than what it has now. And so it's a fun place to be. You're kind of like teased a little bit. It's like, it's kind of like Planck, but not quite. Yeah. Yes. That's really exciting. So so there are people just working on this data now. Like, how is this analysis taking place moving forward?
Yeah, so it takes a long time from the day we said we finish the year 1 data, to take the year 1 data or the year 3 data till the day where we get all the data being processed, and calibrated, and we get all the what we call the source catalogs, and then we get star galaxy separation done, and then we also try to compute the photometric redshifts. And so it takes a long time between the last day of observation and when you actually start to do the cosmological analysis. We also have another step in between, which is the blinding. So with the blinding, we're trying to avoid confirmation bias, and it's actually a big thing nowadays in cosmology. So we blind our results so that we cannot actually say, well, I don't know, the dark energy is a cosmological constant because W is equal to -1, or the matter density of the universe is 30%. We don't know. So we shift this by an amount we don't know, so that we cannot tell the result. And so, this also takes time. And then, you want to really make sure before you do what we call the unblinding, that you're really, you're really sure about what you're doing, so that once you're blind, that's what you're going to publish.
Right. Yeah. So you can't go back and pretend you never saw it.
Exactly.
No, I'm just going to pretend I never saw the way that the data worked out. Let's go reanalyze it before we publish again. Yeah. You mentioned that there's this time period to it, and your advisor or the program leader saying, we're going to take our time and we're going to make sure we do it right, and we might be last but not least, right?
Mm-hmm.
So we had an interview recently with someone who was talking about kind of the opposite side of the race to publish, and how it affected the results, because people were so pressured to publish and so blinded by the ego-driven aspects of the potential of getting a Nobel Prize, or what would come from publishing first on whatever it was. And do you have any thoughts on the competitive versus the cooperative nature of these very large projects like the one you're working on?
Yeah. So in our case, we don't have a competition.
Yeah.
In a way, we are the only ones with the data, and for someone else to try and do the same measurement that we're doing, it will take a long time. So in that sense, there is no competition. Mm-hmm. At the same time, you have to move on. We have to move on because GES has already stopped, and then LSST will start soon. Actually, dark energy spectroscopic instrument, another experiment in which I'm involved, will start this year. And so at that point, what you do, you still have 4 years worth of data to analyze from GES, and then you have the new data. So you want to get going. but I know that it's a different thing from, for example, the gravitational wave world, which I've seen, where you have new discoveries, and that's very, very competitive. And yes, I understand how sometimes that's not the best. I wish there was a balance between these two things. Like,
Yeah.
you want to take years to make a measurement and blind it, and then but yeah, you also don't want to publish something you're not sure about, especially if you're claiming something important about the universe.
Exactly. Yeah.
Yeah, and there's some danger too in having the claims made ahead of time, and then going in and trying to verify them. So I love that this is being done with the proper amount of blinding, so that the outlying data, the outliers of the experiment, are really outliers and just not nonconformists to the assumption. I mean, and it's very important.
Yeah, absolutely. We remember when people claimed the neutrinos were traveling at
Faster than light.
Yeah.
Yeah.
And you don't want to be these people, like, afterwards.
But it did. That one really went back to the old IT question of, is it plugged in? Have you checked the cables?
Yeah, we don't want to get there.
No, you don't. How did you come to get interested in cosmology and this observational side that is so very data heavy?
Yes, good question. Well, I actually started when I was a kid, thinking I wanted to be like an observational astrophysicist. But my father got me this telescope, and I was looking at the planets, the few planets that you can see in Rome, because it's very light polluted. But then for some time, I kind of thought that I was going to become more of a theoretical astrophysicist. So during my studies, that was a bit more of my way. But then somehow during my master's, I started, I was like, I don't want to do anything with hardware. I don't want to build anything. I feel terrible. I just smash things. I'm bad at that. But then you have to pick something for your laboratory. And that's when, I was like, well, I can do something with a lot of data, and it's just programming, and I don't have to touch anything and destroy telescopes. And so that's where I got involved into, actually, that was a Herschel mission, looking at the galactic plane and try to find out about star formation in our galaxy. And so that's how I started being involved, and I actually realized I really liked it. And well, my first passion was cosmology, and so yes, these two things came together, and I started working on cosmology for TS.
Can you give any advice to young women who are interested in astrophysics and cosmology? Physics in general is traditionally a very male-dominated field, and although there are many more women coming into it, it's not always easy. And I'm just wondering if you have any words of advice or of encouragement to young ladies who might be interested.
Yeah, sure. So, don't give up ever. You will. Sometimes you will be treated as if you're not as good as others. I feel like sometimes I have to prove myself twice more than men. Sometimes it's frustrating, but I think there has been a lot of progress being made in the last few years on this topic, and so I think that things are getting better. And so don't give up ever. Keep on believing in what you want to do and what you want to try, and that if your theory you think is right, you should just bring it forward. And I'm sure that things are getting better for women in science.
It just makes me think the having to prove yourself twice, or like do double the work to show that you are an equal. It's like, well, that just shows that I'm better.
Yeah. So are you disadvantaging the women who are coming up behind you by not expecting them to be twice as good?
No, it's brilliant. And what are you in? Like you said, you're going to be moving on to the next dark energy survey that's coming up. Are there any other projects? I mean, probably quite busy with data analysis from this dark energy survey and moving into the next one. But is that just what you're focusing on, or are there other projects that keep you awake at night? Big questions that you just must know things about.
Yeah, well, there's just so many things. The dark energy spectroscopic instrument is, a bit different because it's spectroscopic, and it's also about dark energy and the Hubble constant, etc. But then the big brother of DES is going to be LSST, the Large Synoptic Sky Survey. So this will image the whole southern sky, not just 1/8 of the sky. It's going to be huge, and it will image it like every night. It's going to be just huge amount of data. This is good for a cadence survey. What we call a cadence survey is good for looking at transient stuff. So I hope to get involved with that and look into kilonova events that are associated with the merging of neutron stars. We have tried to search for this also in GES, but LSST will just be so much better for this, and we hope to observe the first, what we call untriggered kilonova event. So we don't get any gravitational wave, but we are able to observe it just from our telescope. So that will be something I'm really interested in.
Do you think that's going to be something like that? The LSST will go online, and do you think it'll be? I mean, what was it? The LIGO Virgo. LIGO came online, and it was like, and bam, black hole mergers. It was like immediately we've got what we were looking for. Do you think that the advanced nature and that large survey and just the time that's going to be given to surveying, do you think that it'll be a pretty rapid discovery?
I don't think so, because I've seen how complicated it is to find this type of transients, and it's hard also once you find it to claim it is that. So I think it will be a bit harder. And we've been so lucky with at least with the binary neutron star event. I feel it's not a way.
I would love to someday look at like a data management and workflow for all of this. Like, it must just be absolute. Like, I bet you there's probably 10 meetings on just data management and how to get it into the right hands and in the right format. Than there is actually, getting to do the analysis on the final data. It must be an intense endeavor just to control how the information is labeled and how it is moved through this workflow.
Yeah, it's just huge. I mean, with DS, we had something like 50 million megabytes of data. And you want to transfer it quickly for the data management people to look into this from Chile to well, in this case, it's in Illinois, at the NCSA, the National Center for Supercomputing. And then there are people there that, are just doing a huge amount of work to process this data, and we have to thank them a lot. It's huge. And LSST is going to be even more massive. Unbelievable.
It's just amazing. And I was reading something today. There's the LOFAR, which is a radio survey throughout Europe. And they've got like something like 20,000 different radio telescopes spread out all over Europe that they're doing radio detection with. And their data, they've got massive amounts of data, and at this point they're still juggling it, and they only have 20% of the data, and of that only 10% is available to researchers to look at.
This is what happens now. We've gotten really good at collecting the data, but it's really hard to move around. So
that's a first world science problem.
It is, but it's also funny because you've got a new project starting this year that you've got to go venture out on, and there's going to be like a generation, ish, but there's going to be a next wave of people working on this project as the data slowly becomes disseminatable to people. So it's kind of awesome in a couple ways, because one, it means the project actually isn't over, that we're going to continue to get good discovery from this. likely for many years to come. And it's not going to slow you down from being on to the next thing.
That's right.
It's something for people to cut their teeth on before they start a project. Is see how you do with this data that was collected over the last 6, 10, 15 years.
Yeah, sometimes I actually have the feeling that we don't get enough people to work on all this data.
Right.
So many things
Yeah.
to do.
Absolutely. So we're coming to the end of our first hour here, and I would love to know if you have any insights from DES or any other work that you've done cosmologically that you think people should understand. Like if there were one kind of insight or take-home message that you think people should understand about this work, what would it be?
At first glance, one might think, well, the universe is so boring. We're just getting what we expected to get. That might be a take-home message if you just look at the results that we got. But at the same time, it's just even more puzzling. Why are we getting exactly what we expected to get? So that's just a big question mark, and we should just keep going and get to analyze all of this data and find out more about dark energy and dark matter.
Thank you. That is such an interesting point too. The why. Now we've got these predictions, these theories, right? And then we're testing them, observing, and it's like it's working out, but we still don't really understand the mechanisms.
Mm-hmm.
We don't know. That's great.
Yeah.
More questions.
It's like the simplest universe also we could imagine, the one with the cosmological constant, like perfect. And we're getting that.
We are, yes, that is the cosmological conundrum, right? That we are, we're here and we're lucky enough to see it, and it's because, and it ties back into it's because it is the way it is, and we have the cosmological constant. Yeah. Anyway, thank you so much for joining us tonight, Dr. Palmese. It's just been wonderful talking with you. Is there a website and are there any social media accounts anywhere that you can send people to find out more about the Dark Energy Survey or to follow you online?
Sure. Well, on the darkenergysurvey.org, that's the Dark Energy Survey website, and you can find a lot of the news, but you can also find it on Twitter and on Facebook, and there's mostly linked to all of our papers there, and also what we call the Darchives, where we explain for the public the papers that we write. And
the Darchives?
The Darchives, yes.
That's great.
Yes, check them out. They're nice. And well, I'm starting just now to use Twitter, so you can follow me there. I'm Ella Palmese. And yeah, I started just recently tweeting stuff about science.
Cool.
Nice.
Very cool. I look forward to following your tweets and learning more as you do. So I think I just love social media for its ability to allow us to communicate with people and kind of that joy of understanding and curiosity that we can share. So I will be following. Thank you so much. I really appreciate your time this evening, and I look forward to hearing more about the Dark Energy Survey.
You will. Thank you very much.
Awesome. All right, everybody, that does it for the first half of our show. We are going to take a quick break, and when we are back, science stories. That's right. We've got all sorts of stories for you. I've got gene drive and genomes. Justin's got bad businesses and
vegetarian dogs.
Vegetarian dogs. That's right. And Blair has old sperm, just in case you forgot. This is This Week in Science. We'll be back in just a few moments. Stay tuned.
Can't explain things you've heard, more than intuition. Alive reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need. Put on a pair of goggles and go looking for the things I couldn't see. The answers lie somewhere within this sky.
Hey, everybody. Thank you so much for your time this evening. I hope you enjoyed learning a bit more about the dark energy survey and all the complicated, wonderful stuff you can learn from light, right? Light carries so much information. It's just fabulous. Thank you to Dr. Palmese for her time. I hope that you are enjoying the show so far. And I'm going to run through my messages so we can get back to our stories ASAP. So I would love to send you to TWIS.org. TWIS.org is where you can find all good TWISy things. That's right. If you're interested in supporting TWIS, head to twist.org and you'll be able to find our Zazzle store where you can find all sorts of items, TWIS mugs, mouse pads, t-shirts, etc. Wonderful products with the TWIS logo so you can share your love of TWIS with the world. Also art from Blair's Animal Corner catalogs. And I think I saw recently that Blair uploaded some new art from the 2019 calendar. So get
I
into
sure did. Yeah.
get into our Zazzle store and look for that to see if there is anything that strikes your fancy. Portion of the proceeds do go to help TWIS. Back at twist.org, you can also click on our donate button. Right along the sidebar, there's a yellow donate button. Takes you to a PayPal interface where you can donate to TWIS an amount of your choosing one time just to help support us in doing what we do as we are listener supported. You can also, if you want to set up a recurring donation, head over to our Patreon community by clicking on that Patreon button in the main header bar. Click on Become a Patron and choose the level of your support. You'll be charged once per month, and you will join a wonderful community of people who are helping to keep this show going, who enjoy the show just like you do. And if you support us at the $10 per month level and above, we will thank you at the end of the show by name. That's right. I'll give you a shout out. It'll be great. And also, if you haven't done so, you can subscribe to TWIS. You can click on the big orange subscribe button or tell somebody else to, and they can find YouTube, iTunes, and Google Play access buttons that make it nice and easy to get your TWIS every week. Additionally, if you go to twist.org and you haven't been there recently, you can sign up for our newsletter. That's right. Next time you go to twist.org, there will be a little pop-up with a sign up for our newsletter. We are putting a newsletter out, and I hope that you want to be a part of that. We want to tell you about all the things TWISy. That's right. We want to tell you about all the things through our newsletter. So please sign up if you can. And if you can't figure out how to do it on the website, send me an email and I will get you signed up. All right, everybody. Thank you for your support. Really, we're listener supported. You are our audience. We do this with you. Thank you for your support.
Can't explain the things you've heard with more than intuition. Alive reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need.
And we are back with more This Week in Science. And it is time for that wonderful segment of our show that has not gone away thanks to all of you.
Yes.
This week in What Has Science Done For Me Lately? All right. John Coleman writes in this week and he says, every once in a while, you hear the phrase, donate my body to science. I have started a business retrieving brains from people who donate their bodies to science. In this role, I have provided brains to research on the cures of Alzheimer's, multiple sclerosis, ALS, multiple systems atrophy, Lewy body dementia, and notably, chronic traumatic encephalopathy in football players and boxers. Science has provided me an ability to work independently and do a thing that not many people can claim. Thank you, science.
That is rad.
So rad. John, what you do is it's valuable, and we thank you for providing this service. I mean, people don't think about what happens when you're a donor, when you donate your organs to science. What does that mean? And it means that there are companies, individuals, companies who assure the transport of those organs in safe condition to places where they can be valuably used for research and can contribute to our understanding of so many human diseases.
It must be
love
difficult.
the idea of my body going to science.
Yeah.
This kind of thing, helping with medical research is really important. Helping train doctors is really important. My personal favorite, if I one day when I die can donate my body to science and put a little clause in there that's like, hey, send me to the body farm. That's actually my personal favorite. I think it is fascinating that you can figure out exactly how long someone has been dead by the species of maggots that are living in them.
I know.
And it's because of people donating their body to science to just let it rot to be able to survey what it is so cool. I'm like, I'm so stoked. I'm so excited to become a science experiment.
That must be a tough job he's got there, though, because you don't get a lot of. You probably have a hard time. I would imagine getting decent feedback from people that you talk to, because as soon as you're like, "Can I pick your brain about something?" They like run.
That's
You're
probably
gonna
their
have to wait
favorite
for
joke.
that.
Yeah. Oh my god.
Yeah, but
Like,
this is
Dad.
this is one of those
science dad jokes.
Yeah, but this is one of those jobs, one of those careers that this is not something that would occur to people. This isn't something like there are so many little roles that are so crucial to the scientific endeavor. And this is one of them. And it's, who would ever think that this could be a job that you could do, right? Keep your eyes open, everyone, because you never know where your next opportunity will arise and where you might find yourself and how you may be a part of science.
Yes.
So, yeah. John, thanks so much for writing in. Everyone else out there, if you haven't written in yet, why not? Come on, share with us what science has done for you lately. It's got to be something. I know it. You don't have to think too hard. It's right on the tip of your tongue. I know it. Send me a letter. I mean, you could send me a letter if you wanted to handwrite it. I have a mailing address.
Letter.
Kiki. I hope this letter finds you well. There's an old sad violin in the background.
Yeah, there's a Ken Burns soundtrack.
Yeah.
I think my violin is more a theremin, I think.
Yeah. Yours is haunted. I'm from the Civil War in mine, and you're a ghost.
Okay, I have an email address, though, that might be easier for most people. Kirsten, KIRSTEN, @thisweekinscience.com. And the other way that you can reach us is to leave us a message on our Facebook page, which is facebook.com/thisweekinscience. Leave us a message. Can't wait to read your note. Can't wait. All right, everyone, let's jump into the science. You know how gene drive is one of the things that we keep bringing up on the show.
Mhm.
Well, there's no new data yet, but an article from NPR that was passed along to me by Pierre, one of our listeners for a very long time. He says he said you need to know about this one. Turns out in Italy there is a research lab which is associated with the University College London lab that performed the research that we reported on at the end of last year on gene drive in mosquitoes being entirely successful in wiping out the lab population because of the strength of the gene that had been edited in these mosquitoes to reduce reproductive capacity in the females. They're using this same system in this Italian research facility. It's a high security lab. So this is no joke. It's high security, which is great. They're taking this very seriously. And they are trying to create an even more real world-ish situation for these mosquitoes, but in the lab. And so they're not actually putting a jungle in the lab, which would be kind of cool. Instead, it's white, fairly sterile lab facility rooms, except with the humidity and heat jacked way up to start to approximate the conditions that would be occurring in countries where malaria is a very large concern, and where these mosquitoes would potentially be spreading disease. And so this new experiment is on its way, and I can't wait to see what happens. You get rid of nice 70 degrees and sunny weather and give it a little bit more humidity and a little bit more heat. What happens to these mosquitoes, and does it change the outcome of the gene drive experiment, I mean. No, I have to say I have a hard time. I mean, I know heat and humid heat. Heat has a very large impact on proteins. Proteins denature at different temperatures, and so there could be an interaction between temperature and this gene drive, the reproductive ability of these mosquitoes. But I think that they need, I mean, really what they need is like predators, and they really need to make it more real world. And I don't think that this one factor, I know it's just adding in one factor. It's kind of like, an elimination diet. You start
you
with
gotta
rice,
add them
and
in one at a time.
then you add zucchini. Yeah.
How does zucchini affect the gene drive? Turns out it didn't, but we had to try.
You had to try it. You had to eliminate all variables. I think this one's tough for me because mosquitoes do well in the heat and the moisture. And so internal processes shouldn't really be affected. So
that's what I would think. Yeah.
Yeah. So if you think about like protein folding and all this kind of stuff, sure. If you take like a chinchilla from the Andes Mountains and throw them into heat, yeah, their internal processes aren't used to being exposed to this variable. But yeah, if you think about the biological processes of a mosquito, yeah, I'm not guessing that this is going to change much.
I mean, there could be different activity by the mosquitoes. So they could be more or less active or something.
Yeah. I mean, that would only make the gene drive more effective if they're more active.
If it makes it more active.
Yeah.
Yeah, so we will see. I just wanted to update everyone, and thank you, Pierre, for sharing this news. I appreciate the tip, and we'll definitely keep people posted, because this is one of those experiments that organizations around the world are very concerned about. And so far, it looks as though these researchers are taking the potential dangers of releasing this technology into the wild very seriously, and they aren't releasing it into the wild yet. They're creating a little bit of the wild in the lab as much as they can, which is cool. Moving on, though, what I thought was really cool is that the great white shark genome has been completely sequenced.
They've been around forever.
Yes, they've been around forever. They're apex predators. They live for a very long time. They grow to massive sizes. Like, these guys can end up like 20 feet long, right? They're these great white sharks are an incredible animal. They dive also. They can dive up to nearly 4,000 foot depths. So they're able to withstand incredible changes in pressure, right? 4,000 feet. That's no laughing matter. I'm like 10 feet. I'm done. That's enough for me.
What is it? I think it's like I might be wrong. 14 every 14 feet is in Earth's atmosphere.
Yeah, something like that. I don't know, but it's not much. Yeah. So this research has come out of a consortium, but it was led by researchers from Nova Southeastern University's Save Our Seas Foundation, Shark Research Center, and Guy Harvey Research Institute, Cornell University College of Veterinary Medicine, and one of my favorites, Monterey Bay Aquarium. They have taken this genome and published the findings in the Proceedings of the National Academy of Sciences, and the results reveal that it has a huge genome. It's 1.5 times larger than the average than a human genome. And it has lots of jumping genes in it, these linear interspersed non-random transposons or elements. And it's also and there are lots of areas of very specific DNA sequence change, positive selection, and the genes that seem to be changing help to keep the genome from mutating. A little ironic there, but what this gets at is there's this hypothesis that very large animals, elephants, sharks, these large animals don't tend to get cancer. And why is that? Why is it that they are not prone to cancer? We get cancer all the time. And what's so different about these really large animals? I mean, sharks can get cancer, but the great white shark can get cancer, but it's really not common. And part of the reason is that they have defense mechanisms within the genome to counteract the accumulation of damage to DNA.
More data management required.
So
right?
also,
We're going back to that again. Yeah.
They just needed a way to manage all of that data, and it got good at it.
Sharks are, I looked it up. I knew it was a crazy number. 400 million years old.
Oh,
so that is a lot of genetic conservation over the years.
Right. But the fact that they are this positive selection, which means these areas of the genome are changing a lot to maintain the integrity of the entire genome, right?
Yes,
we don't want this change to happen. Yeah. So to maintain the stability. But
this is an interesting thing though, because what comes first? Like are sharks because for so long because of this management? Is because everything is just as evolved as anything else on the planet today. We all had a starting point and everything is just as evolved, but lots of us have mutated in different ways and evolved in various forms, more so than the shark. And is it perhaps partly due to a system like this that is conserving?
Yeah. Yep. Researcher Dr. Salvador Jorgensen, a senior research scientist at Monterey Bay Aquarium, who was part of the study, says decoding the white shark genome is providing science with a new set of keys to unlock lingering mysteries about these feared and misunderstood predators. Why sharks have thrived for some 500 million years, longer than almost any vertebrate on Earth. There are other adaptations that are also really cool. They have a lot of genes that are involved in wound healing pathways. So these gene adaptations may explain some of the abilities of sharks to survive and even heal from some pretty damaging wounds. And they've just started digging into the genome, which is the exciting part. There's a lot more that we can learn. And the interesting thing is maybe there are genes within the shark genome that can be used to aid in human health. later. And also, it's the sharks can help humans, but also it's going to help us potentially understand this amazing creature that much more.
Yeah,
Plus, I can figure out how to get some more rows of teeth.
Yes.
Something I've always wanted.
You've got plenty of teeth, and they're fabulous, Blair. They're fabulous.
That's
teeth.
all I want.
You don't need more.
They just keep coming.
So one of the my favorite shark factoids things, which has to be a sort of genetic based reaction strategy for survival, which is amazing in an apex predator, but makes perfect sense, is that when one of them is rendered, classic example is there was that orca attack on a shark, I think off Monterey. All of the white sharks who got that little bit of scent of a shark being torn up alive in the waters left the coast of California en masse, all at once, go away. And
that's how you have to be. If you're an apex predator, you are
something
attuned.
Ate one of you.
You're like, that's a bigger predator than me. I'm out.
We're not gonna fight. We're all gonna just take the summer off and hit it. Boom. I mean, that's such an amazing strategy to have across a species to avoid conflict. I've always appreciated that. Because that's what I would do. I would run away.
I would just run.
If something ate a human, I would just run. That would be my strategy too.
That sounds good. That sounds great. But don't run away here, because I want you to tell me a story now.
This is okay. So this is one of my favorite stories. I teased it in the disclaimer. So around 4,000-ish years ago, Neolithic people of northeastern Iberian Peninsula lived with dogs. And they not only lived like in proximity with dogs, but they were feeding their dogs. And when their dogs died, they buried them. This is out of University of Barcelona study analyses. They did the analysis on the remains of 26 dogs found in funerary structures from 4 different sites and necropolises in the Barcelona region. They conducted isotopic analysis for 18 of them to determine their diet, what they were eating. The highest, so it shows that because there were so many in these recorded in Catalonia, it suggests there's a general practice, and it proves that there was a tight relationship between humans and these animals, which, apart from being buried next to them, they were fed the same diet that the humans were eating.
Oh, they got table scraps.
Yeah, that follows kind of the previous conversation we've had about, did we domesticate dogs, or did they domesticate themselves, or did they really domesticate us because they wanted our food?
Right. So what's interesting about this too is that the humans were largely vegetarian in their diets, and the dogs' diets were also vegetarian. Ancient domesticated dogs had a high presence of cereals, such as corn and other vegetables. And some of the puppies and 2 puppies and 2 of the adult dogs, nutrition was mainly vegetarian, and only a few of the cases had a diet rich in animal proteins.
So what you're saying is this is part of the pro-meat conspiracy that has humans eating meat in every... No, I'm joking.
No, not humans eating meat.
Actually, we also, there's this idea that we need meat with every single meal. And then recently we've kind of learned, okay, it turns out we were eating a lot more vegetables than we thought. This is kind of just the sister story to that.
And unless you're a Neanderthal, in which you were, Neanderthals did have a largely meat diet. Other than that, it's not true ever. And they weren't exclusively meat diet either. But what I think is fascinating is if you walk through, and there'll be I love my kids down the animal food aisle, You know, there's a big chicken on the dog food. That must be
Mhm.
chicken flavored. And then you get to one that's got a cat on it, you know, for the cat food. Oh, that must be cat flavored. Right? Like that must be full of cats in that can.
Yeah.
But they
That's
push
because
like
liver's not very
your
pretty.
dog
No.
was descended from wolves and
Yeah.
needs a good meat diet. No, actually, more chances are your domesticated animal was eating domesticated food, which was cereals and vegetables.
Yeah.
And
That
they
checks
think
out.
that there might have been a side benefit of having the working guard animals eating vegetarian, which is that they wouldn't get distracted when they were doing guard duty or when they were doing whatever tasks that they were put to by wanting to go and chase animals for food, because in their head, like, you know, maybe you're like the dog is supposed to be herding sheep, but instead gets distracted by a carrot that it finds growing somewhere. Like, but for the most part,
I don't think I would ever expect that to happen.
right. But you know what, sideways to the vegetarian aspect, it does sort of explain dogs' loyalty to man, the dedication to mankind, and that fierce resolve to sort of defend their owner. In that these dogs were buried next to the humans. And unless they all died together, that meant that if the owner dies, the dogs all got put down and buried with them.
Yep, that's what I was
and a lot
just
of the
thinking.
a lot of these animals were puppies too. And so you could sort of picture it as the human dies and all the other humans go, well, all of these dogs are bonded to them. They'll never be really my work animal. I'll never be able to right. And so all those work animals go down and get buried, which is also showing reverence for the animals and maybe reverence for the human. But if you're a dog, you really quickly learn that if anything bad happens to my human, I'm getting put down.
Oh,
I'm going to
man.
make sure my human survives
Yeah.
as long as possible. If
Well,
they lose their sight, I'll help them cross the path. If they lose their, like, whatever, if there's a fire, I'll drag them out of the house. I'm going to keep my human alive because I've seen what happens to dogs when their human dies, and I don't want that to happen to me.
So yeah, that's fun, but I mean, it is about selective breeding. A lot of these things, whether it's being done intentionally or not. And you know, one of my favorite stories we've ever done on the show was about how wolves follow other wolves' gaze, their eye direction, and their head direction. Dogs don't really care about other dogs' gaze. They care about human gaze, which means they are evolutionary locked in as a human animal, not a dog animal. So of course it differs breed for breed, kind of when we've bred in. Some breeds are historically very good at communicating with other dogs and being with other dogs. But really the dominant trait in a lot of this breeding that we've done, and again, the first tens to hundreds of thousands of years, depending on what evolutionary history we're looking at, was unintentional, most likely part of it, but especially in this more intentional stretch that we've done, it's all about being focused on and linked to a human.
I'm gonna just do the whiny, high-pitched voice for a moment. As I thought that the wolves actually outperformed the dogs in the knowing what was under what cup or what direction thing. I thought the wolves were better at both human eye tracking and other wolves, and dogs were dedicated to the human vision, but didn't care about that. But the wolves actually outperformed them.
That is a good question. I will have to check. I can check and we can talk about it in the after show.
Okay.
But regardless, my point was that the dogs were better at humans than other dogs. Whether or not dogs are smarter than wolves, you're right. They might not be. They're probably not, because we've done a whole bunch of inbreeding on them. But in terms of my point, I was just trying to say that the dogs were better at recognizing human cues than other dog cues.
That makes sense.
Yeah. And at this point, I think it's time to cue up some music because it is time for Blair's Animal Corner.
With Blair.
Doves are creatures, great and small. Biped, millipede, no pet at all. You want to hear about animals? She's your girl. Except for giant pandas and squirrels.
What you got, Blair?
Do you want to hear about old sperm?
Please.
I think
been
you're
Cover me
waiting.
in old sperm
right.
stories.
Actually, this story is fascinating, simultaneously totally interesting, and a breakthrough and a well-duh moment. And I love these kinds of stories. This is from University of East Anglia and Uppsala University in Sweden. And this was looking at sperm that survived for a longer time in ejaculate versus sperm that died quickly, and the efficacy of that sperm at creating successful progeny. So this was specifically done in zebrafish. So obviously this is a few steps away from human implications as of yet. But they took sperm and in the zebrafish, they can produce thousands to millions of sperm in a single ejaculate, but only a very few end up fertilizing. So what they did is they took some sperm, they took some of it, and in one half they selected for shorter lived sperm, the stuff that that was going to die very quickly, and in the other they selected for the longer lived sperm, the stuff that outlasted the other guys. They added the sperm to 2 half clutches from females to fertilize their eggs and reared the offspring into adulthood. They then monitored the lifespan and reproductive output for 2 years. So they weren't just seeing which created babies. They wanted to see, once babies happened, how long did those babies live? How successful were they in life? And how successful in reproduction were they? And they found that not only does the ejaculate vary in shape and performance, but also in the genetic material, of course. But there was this general assumption that it didn't really matter which sperm fertilizes the egg. It's kind of this grab bag of the male's genes, whatever. But as makes sense, there's this huge difference in the genetic material in the sperm and how they affect the offspring. And so what they found was that the longer lived sperm ended up creating a better lifespan in the offspring, longer lifespan, healthier fish, and they in turn produced more and healthier offspring themselves than the short-lived sperm in the same ejaculate. It's not even like the zebrafish, it was Mondays and Thursdays. It was the same batch, but they took the longer lived versus the shorter lived, and the longer lived sperm did better. So, I mean, it makes sense because it's a higher fitness in sperm. What is the name of the game in sperm? Not just to race, but to outlast, outwit, outsurvive. Sorry, survivor. That's
To
the
win.
job. I'm not here to make friends with other sperm. I'm here to win. So anyway, they outlasted them, and so there's something to that's actually reflecting fitness of the genes inside the sperm.
So then, from a fertility
Yes.
and wishing well on the next generation context, is there a benefit to a longer proboscis, or a lack of having dispensed with the between, like?
No, I understand what you're trying to say. And
I
the
don't.
implication is, he is saying if the copulatory organ was perhaps, I think actually
Larger,
actually
longer.
shorter, right? Because they have farther to go. So the sperm that made it the farther distance would mean they were more fit. That might make sense, but of course, in the grand scheme of things, in the female's organs, that's it doesn't quite work. So this is an external fertilization technique in the
Yeah.
zebrafish. So this is the stuff moving around in the soup that is the ocean, getting to an egg. So I think in this particular case, being long-lived is extremely helpful if you're just kind of sloshing
Floating
around. Yeah, absolutely. So
you want to be around long enough to come into contact or
Mhm.
to find the chemical trail that's going to lead you to the eggs.
Right. I mean, even if you are spawning on top of an egg bed, that sperm's still kind of like floating around in the ocean and has to get somewhere. So there's still something to do there. To extrapolate this to anybody that does internal fertilization is going to be tough because the strategies are so different. I think that has to be the next step if they're trying to bring this to a larger conclusion, which the two things that they bring up as potential applications of this information, obviously with more research, would be for for breeding techniques in livestock. So they think that they could help with that potentially. But the other big thing is if you're doing IVF, if you're doing assisted fertilization as a human, if you can select for the strongest, healthiest sperm, if you're already having reproductive difficulties, maybe you have the sperm chill out a little bit, grab the ones that are still alive, use those in your IVF, that might actually have a better chance of creating successful fertilization. So, of course, this is a lot of what ifs based on a lot of things from a zebrafish.
But not just successful fertilization, optimal offspring.
Yes, super babies. No, it's just successessul. Just getting
it's sort of put a new spin on like when
to be
people
born.
say somebody is a new soul or an old soul.
Yeah.
You
That's an old
must have been an old sperm.
Yeah, old sperm for sure. That quality old sperm. Okay, moving on. Speaking of sexual selection, I will skip to a different story about the amazing creature called the cassowary.
What
Are you guys familiar with cassowaries?
No, of course not. That's why I'm
Oh
going.
my
What?
goodness! So cassowaries.
Tell me about a cassowary.
Cassowaries are a ratite. They are a large flightless bird, like the elephant bird that we've talked about on the show, like the ostrich, like the emu. Cassowaries are from just the very tip of Australia, and they are also from New Guinea and Indonesia. So these guys, they used to have a much wider range, of course. They are being encroached upon because they're a forest animal. They're these big 4 or 5 foot tall ratites, flightless birds, and they have a giant casque on the top of their head. CASQUE, casque.
How do I not know about this bird? Why isn't this
Come to the zoo, Justin. I'll show you a cassowary.
Have you not been to the zoo recently?
Goodness.
Cassowaries are wonderful.
Without cassowaries.
So cassowaries,
their colors are so beautiful too.
They have They have a bright blue face. They have a wattle like a turkey on their neck.
What?
Yes. So this casque is something that has baffled biologists for a very long time because this thing, first they thought it had to do with defense. Then they thought it had to do with foraging techniques, like they could use it to push around stuff on the forest floor to grab. Then guess what? They looked inside. It's made out of keratin and it's hollow and it's actually extremely fragile.
So is it a cooling thing?
Then they thought it was about display. Doesn't seem to be sexually selected for. Then they thought it was about
dinosaur-y.
Yeah, so they thought it was about sound
because
they do make this very low.
Oh yeah, long distance. That's
sound.
A long distance communication thing.
Did not appear to have anything to do with it. The latest hypothesis is, you got it, Justin, all about heat. Yes. So the latest idea is that it is a quote thermal window to help large flightless birds keep cool in hot weather. This is a research project from Australia. And they took 20 captive cassowaries from Victoria through northern Queensland, all in Australia, in different weather conditions. And they looked at thermal imaging. They found that the birds released minimal heat from their cask when it was 5 degrees Celsius and large levels of heat from their cask when it reached 35 degrees Celsius. Now, these guys are warm-blooded since they're birds. They're also covered in black feathers, and some of them are actually kind of hard and keratinized to look. They almost look spiky, but they have this kind of dense, heavy structure. And so it makes sense that they might have trouble with any sort of evaporative cooling. They don't sweat, as far as we can tell. Panting for birds usually means they're really, 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 really hot
Yeah.
and not doing well. So
Not
panting
comfy.
isn't something that they can do. So they think that this is an evaporative cooling technique. So what makes this so interesting is that, as Justin mentioned, they look like dinosaurs. I would encourage anyone to Google the word cassowary feet and look at them. They look like dinosaur feet. They legitimately do. And actually, these feet are used to eviscerate. They can jump up high and come down with these big nails on their feet that are very strong and cut somebody right open.
Yeah, danger bird.
They are a danger bird, absolutely. But so they are kind of these dinosaur-esque animals. They look very primitive, but they also have this cask that some dinosaur species also have. And we know that some dinosaur lineages are kind of in this middle ground between reptile and warm-blooded bird-like thing. And so there is this question of evaporative cooling for especially larger dinosaurs. And whereas, the Stegosaurus or the Dimetrodon have these big fans on their back for evaporative cooling, this could be a more mobile thing that also, who knows, that could have to do with other sorts of displays. But ultimately, that's what they think this is. This is what the science is telling us now, so that it's evaporative cooling. Yeah.
Very cool.
Nice. And it could be various reasons for different species of dinosaurs. And, we can't take this one species, of bird and track it back. But
Not
there
a
is
dinosaur.
not a,
Well,
right?
although
in
that
the lineage, but
related.
The argument of the sounds and the low tone sounds going further with a hollow resonating head ornament is something that has been applied to some dinosaurs as maybe so to have a living example of something that has this morphology and
doesn't use it for that,
right, that's a pretty good clue, especially because it has dinosaur feet. It's
potentially, but at the same time, it's a great clue, but at the same time, we can't take this one data point and say all these other dinosaur species with these features. Yeah, you can't say that.
Which is why we need a real life Jurassic Park.
Yes,
sure. You could also start to look at the distribution of casked dinosaurs on the planet if you only see them in really hot environments.
Very good. Or very large, or if it only seems to show up in very large animals as well.
Also that if you start to see them in colder spaces, maybe that's not what it is. So there's clues that we can do without going full Jurassic Park, but that would also be helpful.
We should still go full Jurassic Park, right?
Sure, why not?
Okay.
Sure, why not? I do have one last animal corner story to quickly close it out, and it is about shrubbery. White-tailed deer are acoustic architects in shrubs. So a recent piece of research looked at white-tailed deer populations throughout North America, and they are on the rise. Why? Because we wiped out all of their predators. And they wanted to see how this affects vocal communication of understory songbirds and other vocal species. They played recorded sounds representing songbird tones and trills and white noise in plots that were either fenced off so that deer were not allowed inside or left open for deer to forage as normal. They looked at fidelity, amplitude, attenuation of sounds across both plots. They found that songbird vocalizations are likely to be more effective and transmit information more clearly where they have deer intensely deer-browsed plots. So it makes sense. They've cleared up all this brush that can disseminate noise, that can kind of like break up the noise. And so open space is an easier place for us to hear things. That makes sense. But the problem is it might help songbirds hear each other. It also might help predators hear the songbirds more. So all we know at this point, for sure, white-tailed deer browsing has acoustic effects that have therefore ecological effects. What they are, we don't know yet. But it's a good reminder, I think, that any animal could be a keystone species. We talk all the time about how this animal's so important. And I feel like all the animals are so important because you're just waiting to find. I mean, the second you remove one, you just find out what they were doing the whole time that you didn't realize. And so deer clear brush so that songbirds can hear each other better. And wolves kill deer so they don't clear too much brush so songbirds aren't eaten. There's this...
And also wolves...
I'm glad
wolves,
that they agreed to all these relationships.
Yeah, I'm so glad they worked it all out. They had a nice long meeting.
Yeah.
Interestingly, too, wolves also keep deer in open spaces because they have the deer then have a better view in open spaces. And when they're in open spaces, they drop more seeds into open spaces, so more forest and brush and shrubbery grows up where it wouldn't have been able to deeper in the forest where they could have been walking around without fear of predator. Yeah. It takes apex to make that. This is exactly my argument for bringing back the mammoth too. As a plant transplanter and a fertilizer of the frozen north.
Yeah, I mean this argument we've had before, but the idea that animals adapt to fill niches in ecosystems. And so when a hole is opened up because of an extinction, it does have reverberating effects on multiple species, but there are often those effects lead to other species pulling up the slack and closing that hole.
And with things like herbivores, if you take out an herbivore, not to say they are less important, they are absolutely important, but there are other herbivores in most ecosystems that can fill that niche. If you take out an apex predator, where's the next one coming from? That's not going to happen for a long time.
Which is why we also need to bring back the saber-toothed tiger.
Oh, sure.
So there's a few steps to actually getting this right.
Justin, there's no understudies in ecology. No. And hire them. Wait, I've got a couple more stories, and then and Justin, you can do your last story in a minute. So a couple of quick stories here. Citizen scientists have been involved in a pretty cool new discovery published through NASA. Researchers have started up through NASA a program called Backyard Worlds Planet 9. And it is a project that has basically been looking in our solar system for stuff like planets, exoplanets like Planet 9, and outside the solar system for objects, brown dwarfs and other objects outside the solar system. And so there was a citizen scientist checking out the data in the project database, looking through it, looking for brown dwarves, and they came across something that looked weird that they thought was wrong. And they're like, there's something wrong with the data. And so they they looked at it again and still were like, what is going on there? They turned it over to the researchers, and lo and behold, it was a very old white dwarf, and it is located about 145 light years away in the constellation Capricornus. This object, J0207, is about 3 billion years old and they figured out that that temperature based on that age based on its temperature, which is just over 10,500 degrees Fahrenheit or 5,800 degrees Celsius. They used the Wide Field Infrared Survey Explorer looking at infrared light, and they found the presence of dust. And so this is the oldest and coldest white dwarf with dust that we have found. If dust rings are found around white dwarfs, it's usually because they're young and they haven't burned up all their dust yet. And so they think that this white dwarf, which should have, blown up and just fused all of its dust and then through the gravitational field, the mass that it had attracted all the material to it and not been left with anything around it because of its age. Well, no, it does. And they think it has rings. They think it has a ring system, which would be a beautiful sight to behold. So citizen science has left scientists scratching their heads as to how this ring system, or it could be one ring, it could be multiple rings. They don't know how it can be. So it's going to lead to some more investigation, which is pretty cool. And then vitamin D. What do you guys think about vitamin D?
Comes from the sun. That's all I know.
Sun.
Vitamin D, it had a huge resurgence a few years ago. It's kind of like this, vitamin D is going to cure everything.
Yeah,
It was like,
Just go outside.
Yeah, well, vitamin D is great. We need vitamin D. It is involved in many metabolic processes within our body, and it is highly involved in cognitive functioning. It is important to brain plasticity, and people who are extremely vitamin D deficient often suffer from cognitive deficits, and deficiency can lead to depression and schizophrenia. So, how does it do this? Well, researchers from the Queensland Brain Institute, they just published in Brain Structure and Function a paper that shows that vitamin D levels influence the integrity of neuronal scaffolding in the brain. It's like they're called perineuronal nets, and they don't go around all the neurons in your brain, but many of the neurons in your brain have these little nets around them. It's kind of like those Christmas light nets that you put over a bush at Christmas time, for Christmas lights, make it look pretty. Well, these perineuronal nets are made of proteins and sugar molecules, and it's a supportive mesh scaffold that surrounds neurons, and in doing so also stabilizes the position of those neurons and their connections, their contacts to other neurons. And in this particular study, researchers removed vitamin D from mice, so not people, but mice, but they found that the perineuronal net in mice that had vitamin D removed from their diet suffered, specifically in the hippocampus of the brain, which is really important to your memory formation.
Yeah.
And also a lot of cognitive function as well. And the strength of connections in between neurons was also reduced. And so they are proposing that normal vitamin D levels are important for stabilizing these perineuronal nets, and that when you don't get enough vitamin D, your brain's going to suffer. These nets degrade and your neurons can't talk to each other as well anymore. Then your hippocampus isn't happy, and then you aren't happy. So,
oh no. So people who work inside a lot, people who maybe, I don't know, have a night shift, this is problematic.
Yeah. So, but this is getting at a mechanism for how vitamin D actually is. Okay, vitamin D is important, but what is it? How is it important? What is exactly that it's doing? And it's like holding your brain together. Vitamin D is involved in like keeping your brain fine-tuned. So at least in mouse brains.
In mice.
Yeah, which it may be the same in people, but we don't know.
Mice need to get more sun.
Yeah.
That's right.
Go outside more, mice. Jeez, why are you stuck inside all the time?
Yeah, and there is also a literature review and proposed mechanism that's also been published in the journal Trends in Neuroscience if you are interested in
I would like to read that. Yeah.
read more of that stuff. And then finally, Lobster Armor.
Ah,
I love this story.
Do you want armor made from lobsters?
I sure do. Smell terrible, but I'll be safe. Pew, pew.
So researchers looking at lobsters are taking inspiration from lobsters to potentially create next generation very flexible protective armor, because lobsters, they've got their little tail that moves and flexes and bends, and it's like these lobsters are motile. They're able to, and their shell protects them, and so does the material that's in the flexible areas. And so they analyzed this flexible connective tissue that connects the plates of the lobster shell together, and they found that it's a hydrogel. It's a natural hydrogel that's 90% water, that has really incredible toughness and strength, and it doesn't crack very easily either. And so they have demonstrated that the structure is also multi-layered, and there's a specific ordering of the fibers within the hydrogel, which are chitin fibers. And those the way that the fibers are all lined up and ordered dissipates energy to make it so tolerant and so strong. And so, seriously, next generation body armor is going to be tough and flexible, and we are going to have an army of lobster men.
Yes.
Yes. Lobstarmer. Lobstarmer. I want to be a lobster man. All right. Justin, what's your last story?
Actually, I have two more.
Get it.
One is missing a link still. We'll find it in the after show.
Get it quick. Let's do it. 5 minutes. Boom. Go.
Okay. I will attempt to speed up the recitation of the final stories. So there's always been a balance that has been struck amongst humans between safety, convenience, and cost. Cars could be built much safer, but become completely unaffordable to the public by having every potential NASA engineered safety feature thrown into it. We could pass a national speed limit of 15 miles per hour, and it would greatly reduce accidents, but the entire society would be horribly inconvenienced. Some jobs are more dangerous than others, but benefits either to the individual doing the job or to society at large outweigh those inherent risks. So, Michigan Technological University researchers asked a question in a much broader context. Is there a threshold in which an entire industry could cross that threshold and be actually doing more harm than good?
Is this about football?
No, but that's kind of fascinating.
This is about the petroleum industry.
Very close.
Okay.
Very close. So, and actually, I would have a hard time not throwing that into this equation. But they kind of did keep some of it narrow. Basically, the metric was everyone has a right to life, everyone has a right to work, and human law should give corporations the right to exist if they benefit humanity. So those are the sort of three matrices, but they did it very one-to-one. They didn't include, I don't think, like wars fought over oil versus, because part of it is like people affected by or people working in oil. That number could be like, gas station attendants. Like it was very difficult. But here's what they came up with. Here's the two that won. And you're very close. Coal industry employs 51,795 people. Total number of annual premature deaths from coal-fired electricity-based air pollution. And this one, too, is like, that's the fact that you could tie it to this. It's probably a much bigger number, but the number is 52,015. So it's about 230 more people die from coal than work
are working.
in
Yeah,
the
that's
industry.
a weird.
Right? It's a weird metric, but it's sort of
Oof.
like, right? Okay. So
Well,
the
it's
metric,
because a certain number of years ago there were more people doing it, and
there
so
were,
they're
right, there
dying
were more
now
people doing
from
it.
what happened before.
But then also, like, I imagine like a lot more coal miners died. Like it might have been, but also like there's like you take into global warming and an increased polar vortex, and you take into account like the radiation that goes out that could be cancers downstream. Like I think the number for the deaths on coal are probably much lower than they actually are. But it's an interesting matrix. The number one should be obvious, but it probably didn't occur to you yet.
Smoking.
Tobacco, very good. The tobacco industry employs 124,342 people. The total number of yearly deaths from direct and secondhand smoke is calculated at 522,000, which would make it a little more than like a 4-to-1 ratio if they hired completely new people every year.
Right.
but it's the same. It's right. It's probably if everybody works in tobacco for 10 years, that 522,000 turns into 5 million.
Right.
So the this is one of the researchers, Pierce, says after running the numbers, the results are shocking. Every coal mining job in the U.S. demands literally one person, one American die every year for that job. For tobacco, it's 4 times worse. And again, this is in that year. If somebody's employed 2 years, it requires 2 people to die in coal or 10 people to die in tobacco. He's making a case for there may be a way you can analyze an industry's cost benefit to society and essentially create legislation that removes it from being an industry that we engage in. My last story of the evening is native California plant makes good. So I mean, plants have been a source of medicine and pharmaceutical for a long time. This is Salk Institute discovery of a potent neuroprotective anti-inflammatory chemical in a native California shrub that they think they can utilize for treatment for Alzheimer's. And this is in the February 2019 issue journal Redox Biology. Quotey voice of senior staff scientist Pamela Mayer. Alzheimer's disease is a leading cause of death in the United States. And because age is a major risk factor, researchers are looking at ways to counter aging's effects on the brain. Our identification of sterubin, a potent neuroprotective component of native California plant called Yerba Santa, is a promising step in that direction. So, this is an interesting line in this press release. At least it says Native California tribes, so Native American, Native Nation folks, dubbed the plant holy herb in Spanish. I don't think that's what they call. I don't think that's when they named it. I think it had another name before that. But it may have been that the Spanish figured out that this plant was very important to the natives. And they liked it for its medicinal properties. One of the things it was used for was to handle things like inflammation. I'll go figure. They kind of figured out that it had this effect elsewhere in the body, right? But yeah, so they had this. This is actually a pretty fascinating study. To identify natural compounds that might reverse neurological disease symptoms, they applied a screening technique used in drug discovery to a commercial library of 400 plant extracts with known pharmaceutical properties. The lab had previously used this approach and identified other chemicals, flavonoids, from plants that have anti-inflammatory, but the molecule sterubin that they got from the yerba santas was the most active component that they came across. And so this isn't yet a human study. It's not that, but this is a good indication. They've got past good discovery using this process, and this is a standout that they think that they're going forward with an animal model of Alzheimer's to determine the characteristics and toxicity. Which toxicity, this is also something that people have used as a tea to some decent potential, and as an extract. It's also like one of those things that you can take a large, dosage of an extract of the plant. Who knows how much of this actual molecule is in that? But then, you don't need the entire plant when you turn it into a pharmaceutical. You can drill it down to certain molecules that you're producing. So if there are side effects that come with the other things that are in the plant, you don't have to deal with them. So it's really a fascinating thing. And it's we've talked about this, has come up a few times over the years, like where they go back and discover something that has been like we had this conversation about cannabis, about discovery of something that's been used for a curative effect for thousands of years, and then for whatever reason stopped because the native culture that utilized it usually got a pressure or whatever.
Yeah, but
and then we rediscover it.
Yeah, there is definitely that rediscovery kind of aspect, and it's like, yay, colonialization, awesome. But the other side of it is getting to the point, where somebody is paying attention and doing a survey of what plants are known to native species to have particular effects, right? And then having the money and the time to do an assay of these plants to find out what they have in them that might be an active compound. And then it's like, okay, it might be an active compound. And some of these things that cultures have taken for years, it could be placebo effect that is a reason they've been taking it. But you don't know until you do the research and study it and find it.
And once you're on the right track, the research will take 5 years. And the other thing is though, there were people going around eating people, and this is always the thing I always think about, like, how do we figure out what we could eat? It's like there's probably pretty important that you had somebody with you when you tried the red berry for the first time, who could report back, don't eat the red berries. Justin's dead. He tried the red berry, killed him immediately. If you didn't have somebody with you, nobody else knows, don't eat the red berry. Somebody else walks around, says he's the red berry, tries it, they die too. That knowledge still hasn't been passed along. But people went around, they must have, eating things in groups and seeing what those effects were. And with no television, no radio, nothing else to do in the day, let's eat everything and see how it makes us feel. Let's see what's going on. So I think we should discount thousands of years of research
we shouldn't.
Of people running around eating things, and should probably go focus back on some of the native indigenous folklore around plants to understand how it got those monikers, because it wasn't casually. And it wasn't.
I think
absolutely.
I think there's one other thing that's kind of analogous to what we're talking about here that I think is worth mentioning, is that there are elements of homeopathy, essential oils, things like this, right? That some of it can be a placebo effect for sure. Some of it might have a basis in something chemical that's happening, and where we can really move forward and make life-saving cures to things is by looking at some of these things and doing the actual research to figure out what's going on. Is there something in this essential oil that's synthesized from a plant that actually, in a more pure version, could have a much larger effect on somebody who is having a problem? So I think that, for all of our jokes about the indigenous peoples, there's potential jokes about trying the berry and maybe dying, but finding,
Oh.
you know, there's logic in some of this that I think has a potential to be out there in some of the stuff that's happening now, but there has to be a desire to do research on some of this stuff. And there has to be a conversation back and forth to kind of figure out what's going on scientifically.
Right. And again, the less scientific aspect of homeopathy and all of that too, you have to also keep in mind, isn't a direct conversation with the native users of those plants and indigenous peoples. It's through a colonial filter of people who adopted something they didn't really understand and then made claims about it. So there's so we also have to remember it's a colonial argument amongst the colonizers about what's right and what's wrong about a thing we don't know anything about.
But I think it has vestiges is all I'm saying, right? It has these kind of almost like fossils of previous methods that there might be something in there, but that's where research steps in, right? That's where research comes into the equation.
Yes,
absolutely. Science. Let's figure it out. Let's see why things are working, how they're working, what are the mechanisms, what is going on there. And what's going on here is that we have reached the end of our show. Thank you, everybody, for listening to the program, to our wonderful interview from Antonella Palmese, and for the stories that we got to discuss in the second half of the show. Thank you to Fada for helping out with show notes, for our YouTube descriptions, and also with social media. Thank you to Identity4 for helping to record the show so that we can have an audio podcast to send out to everybody. Thank you to Gord McLeod for helping out to keep things working in the chat room. And I would also like to thank our Patreon sponsors. Thank you to Paul Disney, Richard Onomus, Ed Dyer, Stu Pollock, Philip Shane, Ken Hayes, Harrison Prather, Charlene Henry, Joshua Fury, Steve DeBell, Alex Wilson, Tony Steele, Craig Landon, Mark Mazzaros, Jack, Matthew Litwin, Jason Roberts, Bill K. Bob Calder, Time Jumper 319, Eric Knapp, Richard Brian Condren, Dave Neighbor, Aiden Jeff, Seth O'Gradney, sorry about that, Stephen Albaran, John Ratnaswamy, Dave Friedel, Daryl Myshak, Andrew Swanson, Paul Ronovich, Corinne Benton, Sue Doster, Dave Wilkinson, Ben Bignell, Richard Porter, Noodles, Kevin Rearder, Christoph Zuknarek, Ashish Pants, Ulysses Adkins, Sarah Chavez, Artyom Rick Ramus, Paul, John McKee, Jason Olds, Brian Carrington, Christopher Dreyer, Lisa Slazewski, Jim Chapeau, Greg Riley, Sean Lamb, Ben Rothig, Steve Leisman, Kurt Larson, Rudy Garcia, Marjorie, Gary S., Robert, Greg Briggs, Brendan Minish, Christopher Rappin, Flying Out, Aaron Luthen, Matt Sutter, Mark Hessenflow, Kevin Parachan, Byron Lee, and E.O. Thank you for all of your support on Patreon. And if any of you are interested in finding out more about Patreon, you can go to TWIS.org and click on the Patreon link. And additionally, you'll find out other things about TWIS while you are there. We will be back here next week, 8:00 p.m. Pacific time on Wednesday night. We have another interview next week. We will be talking with Mike Brown and Konstantin Batygin about Planet 9.
Wow. Fun.
I am so excited for next week's interview. We are going to be talking with Mike Brown, who killed Pluto.
And he was on the hit squad at least, right?
He was on the hit squad.
Gosh, he killed Pluto.
But who wants to give us another planet back? And Konstantin Batygin, who is doing a lot of the work on this Planet 9 issue. So don't miss that show next week. It is going
it's a dwarf planet. Dwarf Planet 9. It's not even a real planet. Why is he calling it a planet?
Maybe not. Maybe not. All right, everybody. So next week, you can join in if you watch us live at twis.org/live. We have a chat room there. We also are live on YouTube, on our YouTube channel. Also a chat room there, so you can catch it live. But if you do not catch it live, don't worry, because we will send it to you if you are subscribed to TWIS. So, yeah, there we go.
Thank you for enjoying the show. TWIS is also available as a podcast if you are into that. Just Google This Week in Science in your iTunes directory. Or if you have a mobile type device, you can look for TWIS, the number 4 Droid app in the Android marketplace, or simply This Week in Science and anything Apple Marketplacey.
Are you looking for more information on something you heard here today? Show notes are available on our website. That's right. It's at www.twis.org. Hey, while you're there, you can also make comments and start conversations with the hosts and other listeners.
But if you don't want to do that, you can just contact us directly. Email Kirsten at thisweekinscience.com, Justin at twistminion@gmail.com, or Blair at blairbaz@twis.org. Just be sure to put TWIS, TWIS, somewhere in the subject line, because if you don't, your email will be immediately spam filtered into a... You can also hit us up on the Twitter, where we are at TWIS Science, at Dr. Kiki, at Jackson Fly, and at Blair's Menagerie. We love your feedback. If there's a topic you would like us to cover or address, a suggestion for an interview, a haiku that comes to you in the night, please let us know.
We'll be back right here next week, and we hope you'll join us again for more great science news.
Yes, because if you've learned anything from this show, remember,
It's all in your head.
This week in science. This week in science. This week in science. This week in science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. This week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got one disclaimer and it shouldn't be news. That what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just get understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. And This Week in Science is coming your way. So everybody listen to everything we say. And if you use our method instead of rolling a die, we may rid the world of toxoplasma. Got the eye. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got a laundry list of items I want to address. From stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. So how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say, and if you learned anything from the words that we said, then please just remember it's all in your head. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 This Week in 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 Science.
Blair.
Mm,
Blair.
yes.
I love the Dimetrodon pillow.
Yeah. Hey, click on it. Click on it and look at the back.
Oh, what is it? Ooh, look at that. And it says
Bam.
twist on the back. Oh, I love that. Look what you did there. Look at that pillow. Dimetrodon twist pillow. That is so cute.
Did you see the kiwi purse also?
I did. Yeah. I love, look at this little purse.
Look at him go.
And then look at the twist and the kiwi. Oh, it's adorable. I love that. And it's on both
I
sides.
had fun. I had fun.
Yeah, you did. These things. And for those of you who absolutely must wear a tie to work,
Yes. Which one
maybe,
did I put on there? Oh, the
mayhaps,
sea turtle.
mayhaps, you need a sea turtle.
Yeah.
Look how fantastic that is.
That's a goodness. I had fun. And the
Yeah.
inside of the tie says twist.
Oh, wait, what?
Yeah.
Oh, look at that.
Branding.
I love that. That's
I had fun.
amazing.
I put on one of my favorite movies, A Mighty Wind, and I just messed
love
around
that
in the Zazzle
movie.
store for the whole film.
Oh, that's awesome.
Yeah, I made a laptop sleeve, as you can see, and a phone case.
Mantis phone case. There
Mantis
you
phone
go.
case.
Yeah. I love that.
Mhm. I had a good time.
Yeah. Oh, I think it's great. I think we should, there's this huge, like, these products are awesome. There's this huge movement right now. I'm not so into it myself for my own fashion choices most of the time, but there are all sorts of people who want to wear science-y fashion.
Mm-hmm.
You know, I feel like we're addressing a little bit of this here. I seriously, the T-Rex tie, this is
Yeah. I like that one a lot
this
too.
is just
Oh my god.
it's just awesome. Yes. I could say twist.
Ugh.
And the wrapping paper. Are you tired?
I'm sleepy. Summer zoo camp registration opened today.
Oh, okay.
And so I was on the phone for about 4 hours answering
Questions.
phone calls.
Questions.
Yes.
Yeah. Where's Justin? There's Justin. So Justin, I was thinking about your last story about like was it last story? No. The cost benefit analysis.
Oh yeah.
And was thinking, I mean, people are getting real down on sugar these days. I mean, if you were to think about metabolic disease and
like fast food.
Yeah. Sugar. Like
Well,
is it as easy to connect sugar as tobacco to deaths?
So
death by sugar.
Right. One of the things, like anything diet related, you have to realize that we don't know anything yet, and it's microbiome. And one of
and genetics too. Like genetics is part of it. Yeah.
Yeah. But and one of the sort of examples that sticks out in my brain whenever I start to think about what does diet mean is like people from Hawaii and Fiji exposed to a Western diet gain a lot of weight. More so maybe than like somebody like myself who may have ancestry or genes or a history of microbiology associated with fast food restaurants that does not get affected in this way. You know, you look at like, well, you need a well-rounded diet. You have to have plenty of vegetables, except the Inuits in Greenland have no access to vegetation and they're doing just fine.
Right.
So that, you know,
there's also variables. Yeah.
There's variables in evolution and in adaptation to region and everything else. So there's a much bigger conversation that eventually we will get to where we will be able to determine whether or not sugar will affect you negatively, whether
Yes.
or not
Yes.
excessive alcohol use is something that is excessive based on your genes, whether or not exercise is something that your people really engaged in a long time, or whatever the scenario is. These things are going to have different affects to different populations. And as these peoples of the earth merge and meld and build upon their genetic code and have reliance on medical advances,
Right.
we're going to look for more alternatives to evolution because that won't be serving us in our environment.
Right.
So
So-
yeah, so it's with smoke, for example, like it's very easy to know because you have a built-in control of smoking versus not smoking, whereas
Right,
eating
everybody
is something that everybody does.
Yeah.
but
So
there
it's an
are
interesting study.
even there's even confounding there is, I mean, smoking aside, but there is even some confounding evidence there or information there. Smoking kills people. I'm not detracting from this. But when you're talking about causes of cancer, we know that they spring from multitudes of places. And so as we are at the same time reducing our smoking as a society in America, we're also removing those carcinogens that were preventing mattresses from catching fire, because those were carcinogens. Why'd we have them there? Because people smoked in bed and started fires. So there's like a lot that's moving together in this sort of awareness of carcinogens that will largely be associable to smoking, but we're also making a lot of other progress in a vast bevy of carcinogens, and understanding that, you know, maybe it's not great to wash those auto parts in the diesel fuel without gloves on, right? Like, we're learning a lot that we didn't take into account for so long, that we should be reducing cancer rates.
There's this whole thing that I went to a Science on Tap here last night to check out the theater where we're going to be doing our show.
Woot.
And the woman doing the talk last night was talking about the microbiome, and she was fantastic. And her one of the points that she made, she's like, food with preservatives in it. You know, it's like we talk about processed food, but what about food that is made to sit on a shelf for a very long time without molding? That has preservatives in it that are meant to kill bacteria, to keep bacteria from growing. And so when you eat that,
hey, you're killing bacteria in your tummy.
You're killing bacteria in your tummy. And so this is one of those things where people are like, processed food is bad, but they don't really talk, you know, it's like, oh, well, sugar and fat, and they talk about that kind of stuff, but they don't talk about the fact that very often there are these preservatives added to food, which actually may be worse for you than the sugar and the fat and the
By the way,
flour,
do you know what bacteria love to eat? Sugar.
Sugar.
So I mean, so this is the thing. Like, it's such a, this is the argument that I know I've told on this show like a dozen times, that I had with my my dentist, or my oral hygienist that the dentist brought in to talk to me about, you know, knocking out the bacteria that are in your mouth causing plaque. Because I get,
we've talked about this. You want the competition, right?
Right.
Yeah.
I get the rapid plaque buildup, but I have like no cavities. So my argument was, why would I knock out the bacteria? That I get it. I have to come in here. You got to scrape and chisel to get the gunk off there every once in a while. But why would I get rid of that if that is populated and prevented the bacteria that causes cavities from having a foothold in my mouth? Why would I ever want to destroy that balance? I like the fact that I can come and get cleanings and no drilling.
Yeah. But then there's the other thing she brought up that was really interesting is the that personal hygiene products are not monitored or have never really been studied for their effects on the microbiome.
Like
We're
like
putting
deodorant.
deodorant, lotion, just all these things that we're everything that we put on and in our
and
bodies.
I will throw into that.
It's
I will throw
affecting
Yeah.
our superorganism.
I will throw into that the all natural
I don't like
hygiene
being
products
stinky.
too. Like what is it? Is it lavender is a synthetic estrogen?
Right?
Oh yeah.
Yes.
So I mean,
there's
like
all sorts of things.
even that whole natural versus man-made
Yeah.
component that you're putting on your body,
We
like
still don't
just sweat
know.
and
Yeah.
smell like a human, people. Come on.
Well,
All
and then
right.
there's the
We're
weird
all
thing
in
where
it.
like people who don't
No,
wear
just
Just change your
deodorant
socks.
say they
Change your
like
socks.
a lot
There
of
you go.
people say they don't need deodorant, and so they don't wear it, and like people who do wear deodorant, they create a need for it, right?
Mhm.
But so there's some of that happening, but there's also some of like maybe you just don't wear deodorant because you don't need it. So it's like pretty hard. Like maybe
Yeah.
some people's microbiome in their armpits is really stinky. Like maybe
Uh-huh.
that's just their natural
different.
state.
Some
But in
people-
some cases, I will say in my own uncontrolled experiment, I have noted that when I used to wear underarm deodorant every single day, I noticed immediately days that I didn't wear it, I got sweaty and stinky.
Okay.
And when I stopped putting it on every day, it was a tough few weeks. But then it started to kind of like re-equalize, and it's not as much of an issue for me anymore.
Deodorant
I
is
do-
different. Deodorant's also different from antiperspirant.
Right.
So like
Which I don't
even
use antiperspirant.
you're gonna get sweaty if
Yeah.
you're wearing deodorant, no matter what.
Mhm.
If you get sweaty, but the
Yeah.
odor is gonna be affected.
So I only wear deodorant if I did the armpit sniff test, and I'm like, I should probably knock that down.
Yeah.
It's the only time I've ever put it on.
Exactly. Yeah.
That's what it's for. It's to knock it down. It's like I could go and, but there is a bacterial component to this too. So like, if you are like, if everybody's saying like your BO has got to go,
Hey, stop
that
cooking
might be
onions.
the one excuse to use an anti-bac soap on your pits. I'm just gonna give you. It's like using an antibiotic. Like only do it if it's absolutely necessary. Don't use the antibiotic soap every day because then you'll never get anything else that can infiltrate.
Yeah.
But if it's really like I just showered and my pits stink, it might be the one excuse to allow a little triglycerin.
Yeah, I had a recently I just grabbed whatever product. I was out and my normal antiperspirant deodorant was not at the store. So I was like, I'll just grab this one. And it's close enough. I couldn't stand the smell of myself. And I would be like, I'm like, what? Like, and it was like a week and I was like, I smell wrong. And so I don't know whether it was, it's my bacteria interacting with this new deodorant. And I did not like it. I was like, this is the worst. I was uncomfortable and unhappy for like a few days until I could get back to the store and buy what I needed. I was like, oh my God, this is the worst.
Really interesting. But it's also like, because we become, I think, nose blind to an extent to our own sense, right? And I think you become nose blind. Well, but I think you also
I don't want to smell myself all the time.
No, right. But I think people also become nose blind to their covers, their deodorants, their antiperspirants, their colognes or perfumes. They can become nose blind to them to the extent that, whether you have really bad BO and don't know it, or your cologne is like magnitude more than you should have applied and you don't know it, you are nasally offending people in both those directions. And I think it's interesting that when you did that switch, you were acutely aware of a scent that you might not have been with your regular brand, but it might have been as strong. Like this is like an interesting.
I'm very aware of changes in how I smell. So I find it when I eat I don't know if
Great
I've
comment.
talked about this before. When I eat curry, food that has curry in it, like I will smell like I'm like, I smell like curry. And I wander around going, I smell like curry. I smell and I ask my husband, do I smell like curry? And he's like, no, you don't smell like curry. And I'm like, I smell like curry. I can smell it.
The one that does that for me is if I accidentally ingest cinnamon, which
Right.
I think I've explained in the past. For some reason, is in my brain the same smell that I smell when hair is burnt.
What?
It's like horrible. Cinnamon is the most disgusting smell. There's like cat urine is like an 8 or a 9,
Oh,
and
geez.
then cinnamon is 10. And
Wow,
it's like the worst.
I made snickerdoodles yesterday. You would have hated the smell of
Oh,
my
no, I
house.
totally would. I wouldn't have been able to come to your home. But every once in a
Wow.
while,
You'd be like,
I'll
nope.
eat something, not realizing there's a cinnamon component to it because I just didn't. The olfactory didn't kick in time, and then now it's like I'm like emanating like
Yikes.
cinnamon with every breath, and I have to find something to cover it up. Ugh, cinnamon's just so gross. Humans, stop it. And every Christmas, there's like cinnamon sprays, which I don't know if the general public notices. I definitely noticed.
Oh no,
No, it's
yeah.
all over.
And during the
It's
fall, they
holiday
have the
smell.
cinnamon broom. The
Yeah,
cinnamon
yeah,
broom is a
cinnamon
big
broom,
thing.
But
Yeah.
the flower area, the poinsettias in any like the grocery store, like horrible sad flower area, they do a spray of cinnamon on the poinsettias to make you think about Christmas when you see a poinsettia. And they start adding cinnamon scented stuff to like movie theaters, like it shows up everywhere, and I'm like, I'm like acutely sensitive to this one particular.
You need to go to a non-cinnamon country for the holidays. No
Yeah.
cinnamon.
Yeah.
No cinnamon on this
Yeah.
island.
I don't know many places where there isn't cinnamon.
Everywhere. It's
Yeah,
everywhere.
it is
Hey,
everywhere.
Blair, did you ever manage to Google whether or not wolves can
Oh.
track?
Yeah, no, I
I
forgot.
feel like we've had this conversation. Like I'm deja vuing as if we've had this like 2 or 3 times, but apparently neither of us remember the result of the conversation.
Yeah, let me go to twist.org to see if I can find it because I want to find like. I'm gonna go
this
wolf.
was years ago. Oh my gosh, this would have been a 2012-ish story.
No.
Yeah, it was that long ago. And the only reason I know is because I was where I was living there. We had a dog that I always think of when I think of that story, and because at the time this is how my brain works. It's also how I remember what year movies came out, because I remember who I went to the movie with.
Oh, dog directions. I feel like that might be it.
I think that has to do with pooping north to south.
Anything at all.
Yeah, you're right. That's what that was.
So we are confirmed for April 3rd.
Immediately tells me what that story is about. That's kind of funny.
April 3rd. April 3rd, everybody. We're confirmed. We now have a theater, the Alberta Rose Theater in Portland, Oregon, on April 3rd for the live TWIS show.
I booked my flight.
Yeah.
I haven't. I might drive up. Who knows?
It's a long drive. You better get here in time for the show. You can do it.
That's hard. Call up, be like, "Hi, do you have airplanes to go to Portlandia?"
And they'll be
Not
like,
on
yes,
your
we have several every day. And I'm like, give me the early one so I can get there and have time
Then
to
I'm
be
gonna
there.
book it to PDX, and I'll end up in Phoenix. And,
Don't go to Phoenix.
find a hotel with good Wi-Fi.
Okay, let's see.
What do you mean you don't have Wi-Fi in Phoenix?
Dogs are able to follow human gaze. Okay, this is from 2015.
15. Is it wolves versus dogs? What's it
Hold
called?
on, I'm reading it. Let's see. Dogs may present as special cases. We find evidence that they are able to follow human gaze to objects such as food or toys, but not for the comparatively simpler task of following gaze into distant space. No. No, this isn't it. This is the same thing. Okay, so wolves following human gaze is in 2011, but it doesn't appear.
I was off by
But it does not appear to compare it to dogs at all.
Oh.
It's just saying, hey, wolves follow human gaze.
Okay, so the version of that then was the following year because I remember 2012. So I have to be right?
This from 2014 says 25 canid species, comparing variations in facial pattern and coloring, observations about their social behavior, evolutionary history. Canines use facial markers to highlight or de-emphasize the eyes. Species with more distinguishable eyes live and hunt in groups, where gaze communication facilitates the teamwork that is necessary to bring down large prey and stay safe. Those with camouflaged eyes are more likely to live alone or in pairs, where communication with other members of the species may not be needed in the same way. That's pretty interesting. But not really an answer to this question.
Okay.
Gaze communication. Previous studies have shown that domestic dogs are more likely to make direct eye contact with humans than wolves raised in the same setting. So that's something.
Hang on.
So dogs are more likely to make eye contact with humans than wolves.
So this is also follows though. Check this out. The wolves aren't different. This is December 3rd, 2013. Domestication of dogs may have elaborated on a pre-existing capacity of wolves to learn from humans. In this study, what they demonstrated that wolves were less likely to follow dog demonstrators to hidden food than humans.
Wait, say it again. Wolves were more likely to follow dogs?
No, wolves were more likely to follow humans than the dog demonstrators.
Oh, that's interesting.
So it sort of builds off that one that you were talking about, but it's like they are tracking, like they both actually track us more than they trust each other for the wolves and dogs. This is interesting. This is actually kind of finding a middle ground. Wolves and dogs were 2 to 4 times more likely to find the snack after watching a human or dog demonstrator hide it, and this implies that they learned from the demonstration instead of only relying on their sense of smell. Moreover, they rarely looked for the food when the human demonstrator had only pretended to hide it, and this proves that they had watched very carefully. Wolves were less likely to follow dog demonstrators to hidden food. Does not necessarily mean that they're not paying attention to dog demonstrators. On the contrary, the wolves may have been perceptive enough to notice that demonstrator dogs did not find the food reward particularly tasty themselves, so simply did not bother to look for it. Interesting.
Okay, so I found a couple other interesting things. Scientific American in 2017 say when a dog gazes deeply into the eyes of a human, extended eye contact triggers the same hormone responses that helps human mothers bond with their babies. Aw. So oxytocin floods the owner's brain, and there's a similar spike in the dog, which is neat, but not an answer to this question. Dogs, but not wolves, use humans as tools. This is from 2012. Let's see. Where's the actual research? Come on. Ooh, doo-doo. Okay. Hand-raised group of dog puppies and a group of wolf pups from birth, resulting in roughly equivalent experiences. At differences between the two groups' social cognitive skills. Oh, any differences between the two groups' social cognitive skills would be attributed to genetics at that point. From 6 days after birth, before their eyes had fully opened, they started interacting with humans. Okay. A plate of food was presented to the wolf pups or the dog puppies. The food was inaccessible to all the animals. Human help would be required. The trick to getting the food was simple. All the animals had to do was make eye contact with the experimenter. That's cool. He or she would reward the dog with food from the plate. All the animals attempted to reach the food. By the second minute of testing, dogs looked at the humans. This increased over time, and by the fourth minute, there was a statistical difference. Dogs were more likely to initiate eye contact with the human than the wolves were. Okay. Also not answering this question, but it's
Right.
along similar lines.
So here's one from 2017. Wolves understand cause and effect better than dogs. Okay, where's the quotey thing? Both dogs and wolves were able to follow communicative cues to find hidden food. However, without direct eye contact, neither the dog nor the wolves chose the correct object. In the absence of a human to show them where the food was located, only the wolves were able to make casual inferences. In this experiment, wolves showed an understanding of cause and effect which the dogs lacked. So, that's not reading humans any better, but it's just about being more clever.
It's just really hard to search for dog v dog versus dog v human gaze, you know? But I swear I read something about that at some point.
This has been studied a lot more than I thought maybe it had been. So it's still an open question. But basically, I guess the underlying point that I could ground this on is that there doesn't really seem to be a huge advantage for these thousands of years of coevolution of man and dog being able to communicate. It really looks more like wolves, and then they're off, and the lineage that came. It's just clever, and maybe it's just we all. It's maybe it has less to do with cohabitation, but is the reason for the cohabitation.
Yeah,
is that we adopted similar communication cues around similar understandings of our environment, and that's why the friendship started in the first place.
Yeah, I think that it's really popular to talk about like, oh, well, cats domesticated us. Like, cats are not domestic. I kind of agree with that. Like, they definitely don't need us. They could get by on their own. But the second you kind of shift the perspective that way, it really sounds like dogs also domesticated us. They were kind of like, hey, here's the deal. I'll give you companionship. I'll do utility things for you. You're going to keep me warm and feed me. Like, it really seems like, because everything that we kind of know about the hypotheses of how dog domestication started was with dogs coming towards us, not us going towards the dogs. The dogs started reducing their flight distance over time as there was more and more food and warmth and shelter near humans. So they kind of domesticated themselves. They were kind of like some of the wolves were like, I'm gonna go hang out with them, and it worked out for them. And from there, it kind of, it progressed. But I think that there's this narrative of like, man wanted companion, man lured in dog became
cute.
companion.
Puppies are cute though.
Yeah.
And it does, and like people are like kind of affectionate toward baby animal anything.
Well, exactly my point. Like other things haven't been domesticated that are cute as babies. And wolves will kill you. Like there is this disconnect where this is a really dangerous animal. How come it didn't attack humans when humans started getting closer to it? Because they were already self-selecting for being calmer around humans.
So here's what I kind of think is interesting, and it's a bit of a chicken and the egg, but we all know it's the egg that came first. Wolves are hunters, and humans did persistence hunting, and then if they were in the Neanderthals, they did the up close hunting. And where domestication happened is in places where Neanderthals had been for hundreds of thousands of years. And so the question is, who's the better hunter, and who comes and scavenges after? So the wolves make a kill. Humans notice this. They wait till the wolves have had their fill, and we slowly sconch in.
See, we were domesticated.
Wait a second. But on the other hand, Neanderthals made big kills, and they could only carry so much back. And so who's waiting around for the humans to start to kind of back off with the finish with their kill? The wolves. And so there's this interesting sort of dynamic of both being hunters, both making these big kills, and the other kind of moving in. And so we sort of shared a lot of territory in these sort of scenarios where we weren't the interest. We weren't the party of interest. We weren't predator or prey. We were both sort of sharing it. But then also fascinating that then once domesticated, we're like, okay, you're now eating cereals.
Right. Well, also, if you think about it, like the human predecessors, their teeth were kind of, I mean, they're definitely better than ours, but not great for eating meat. So I feel like they left a lot of scraps. And
yeah, although we do also have interestingly, like a lot of evidence of stone tool use to break bones to get to marrow.
Yeah. But there's still something for the dogs to chew on. There's still something. Yeah. And anyway, Ed, I disagree. There are definitely dogs that want you to stare lovingly into their eyes for all of time. They're called golden retrievers and labs. They just love it. No, there's lots of dogs actually that really enjoy eye contact. That's the thing I was just reading about oxytocin. Apparently there's an oxytocin spike in both dogs and humans when they stare lovingly into each other's eyes.
Whenever I do that, I say to a dog, don't eat me. Oh, don't eat me. Ah, don't eat me. And they get it on I think a lot of levels. Yeah.
So
anyway.
Okay. Well, I think I've reached the end of tonight's episode. Blair is yawning ginormously. So I think it's time for you to say goodnight, Blair.
Good night, Blair. Say goodnight, Justin.
Good night, Justin.
Good night, Kiki.
Good night, everyone. Thank you so much for joining us for another episode of This Week in Science. It's late, everyone. Go to bed. Or don't. Stay up and do what you need to do. We'll be back. I'll be here. I'll be on Twitch on Friday at 1 p.m. for my Twitch stream. And we will be back here next Wednesday and are looking forward to it. You signed up for a newsletter. I hope you got one this last week.
Yes.
Yeah, I hope you got one.
Hippo Day.
for Hippo Day. And we'll be sending out another one again soon. So we'll be in touch, everyone. And if you haven't signed up for our newsletter, sign up for our newsletter. Okay. We'll see you next week. Wait, how do I turn this thing off? I have to hit the stop broadcast button.